which is by Miguel. I'm trying to retrieve. Miguel, why don't you share your screen while I find my list? Here it is. So Miguel, I'll give you a audible 1 minute to your 12 minutes, okay?
All right, thanks. All right. Hi, everyone. My name is Miguel González. I'm a student, second year student at the PhD in Macquarie University. I work with my supervisor, Orsola and Marco, and our collaborators, Mike Lau, Daniel Price, Ryosuke Hirai, and Ilya Mandel at Monash University. And I'm going to talk about common envelope evolution using thermally pulsating AGB stars as donor. Okay, first of all, what is a common envelope? Basically, as Orsola said before, is this event in which you have expansion of one of the components in the binary and engulfing the whole system, right? So first you have the normal binary, as you can see normal, and then you have an initial mass transfer due to the Ryosuke overflow, and eventually you have the common envelope. Now, the next thing I'm gonna show you is a small movie I made about one of the modules I'm gonna show you later. And here you can see the whole process taking place. First, you have the mass transfer, and as the mass is being transferred, you have a transfer of angular momentum from the companion to the gas, which makes the companion closer to the donor, which in turn makes this makes it closer, which makes a more transfer of gas to the outside, and then you have a closer separation between the binary. Until eventually you reach this spiral phase in which the star is already going in an orbital shape, right? In this point, basically half, a good portion of the material is mechanically being unbound from the system. And after this, what you have is in this case, in this structure, because the gas is being, the outer gas is being expelled. However, this will not remain unbound, and it will supposedly be optically thin. The structure we care about is more about the central one, because that is the part when we have the post-common envelope, the post-common envelope more structure that would become the planetary nebula, right? Now, so what well, basically, for doing this kind of simulations, typically it's been used RGB stars donor. And recently, both works on Sand and Shamandi have been using early AGB type stars. However, in this work, we are using a thermally pulsating, which is in the late phase of the AGB star evolutionary as a donor. And we put a 0.6 solar mass companion. Here in this table, we just put the summary of all the binary parameters for Shamandi, Sand, and this work. You can also see that the codes being used are AMR, moving mesh for Astrobear and Aripo, respectively, and in our case, a phantom. However, all the three stars were the initial star, the donor, was created and evolved using the MESA code, which is grid code, right, in 1D. Now, our primary thermal pulsating AGB star, talking a little bit about the evolutionary phase, we have this, we chose this particular moment in the star story because this is the first time that it reaches these values in size. What do I mean with that? What do I mean with that is because the RGB phase reaches typically around 100, like 80, 90 solar radius. But in this case, this is the first moment in the red point we're showing here, in which the star reaches a value around 260 solar radii. And following the blue dashed line, you will see that it will keep expanding for around 200 years and then contracting another 200 years, which makes this star with a size of 260 solar radii as a minimum for a time of around 400 years. So this is important because if you have this star in the system, the binary system, and then it reaches the Ryosuke overflow, which shows, for example, the 260, then it will overfill it, and then will keep expanding, and then the material will be transferred to the companion, and that will trigger basically a mass transfer, and with that the common envelope. So that's the reason we chose this particular moment. Now the question is whether the whole common envelope evolution can take place during this thermal pulse around these 400 years. So the first thing we did obviously was after we created star mesa, we mapped it into the phantom, and we choose a new stabilization procedure by law. This is typically the normal thing we do is just to replace the center of the star by a point mass particle. In this case, we choose a value 0.56, a solar mass point mass particle. And we relax it over several dynamical times. Now, we did a little test of stability because remember, this star, the reason we never use this kind of stars, one of the reasons is because it's really difficult to stabilize this kind of models because they are really they are really expanding, as you can see, and also because well, that's and because it's not well understood how the thermal pulse is taking place. However, we know that at this moment the MESA code can model up until a certain point these values. So what we did is basically running 3 different models, ideal gas at low and high resolution, and using the MESA equation of state, which gives also recombination. And then we compare the isolated models, just let it go, evolve in phantom for a certain time, well after the dynamical times, which is by the way around 0.2 years, which is, as you can see here, is comparatively really at the beginning of the model, not around 14 or 15 years. That is, well, we are not running this quick stabilization test and to see how was the growing of the system. You can see that the MESA model and the DL gas at low resolution have highest expansion rate to compare to the MESA model, which is the dashed line. However, the ideal gas at high resolution, it's growing slower, which basically gives this kind of limit, upper and lower limit of the expansion of the star. The squares that you can see here are the points in time of these particular models in which we chose to take the star and put it in the binaries. Anyway, like I mentioned before, we use these 3 models. For the low resolution, we use all around 0.13 million particles, then 10 times higher for the high resolution, and the same value, 1.3 million particles for the MESA tabulated equation of state. Now, once we run it and we check for the orbital evolution to try to answer the first question, whether the whole system can take place in certain, and at least for the simulations, the answer is yes. The 3 simulations takes around before the high spiral phase, which it's at most at 15 years, are being taking place, which means that all the whole evolution is taking place around 1 order of magnitude smaller than the whole thermal pulse, which is really good for this work, right? And then we know also that something that we already knew is the fact that the resolution defines in a way or influence the speed at which we pass from the mass transfer phase to the spiral phase. That's why the high resolution ideal takes a little bit more time to get to the spiral phase, right? Whether the MESA 1, which is a little bit more close, but we'll see eventually, since it had more internal energy, it's a little bit more expanded. Therefore, it takes place in a smaller time scale. We also noticed that the final separation of all the models pretty much is similar. It's between 20 and 30 solar radii for these 3 models. And okay, now going to the bound mass, the question whether it will unbound or not the envelope, we have these 2. Sorry, we have this plot for the MESA model, in which we can see that the star is being unbounding around 80% of the total mass of the bound of the system, right? We are using these 2 different criteria, which is potential and kinetic. which is basically the mechanical criteria, and also using the thermal energy as defining last. If we have the sum of these three quantities is larger than zero, then it's been unbound, right? Right after the spiral, we have that the mass bounce radio for the ideal gas is around 0.0016 solar masses per year. Now for the morphology, we compare our results with the work done by Rickard 2020, in which we select a particular snapshot of the simulation to compare how is the morphology of the post-common envelope system. And we found that it's a little bit more, that the size of the AGB is typically similar for the ideal gas, but it's a little bit more expanded for the MESA 1. However, it still is a little bit more larger for the AGB. The black contour shows the value at around 1 to the minus 9 grams per centimeter square, which is the value that we select for choosing if we keep cooling down a faster radio. Basically, inside this region, we have the radiation is high enough and the density is high enough so that it's not contracting due to the cooling. So this result basically tells us that the common envelope is taking in around 20 years compared to the 400 years of the pulse period. So this means that the common envelope evolution can take place during these thermal pulses, and therefore they are really great candidates for common envelope donors. The unbound mass fraction between the MESA 1 and the ideal one is between 17 for the ideal gas and 82 for the MESA equation of state. The recombination is definitely taking a place, an important role. However, it's really unknown. It's really unknown if it can be retained inside the gas, as Orsola said previously. Now, the AGB shape of the post-common envelope system is a little bit more puffier, expanded. However, it's a little bit more well-defined compared to the ideal gas, which is, and we know that inside this region it should be optically thick. For the future work, we have that we want to test the thermal pulsating for higher mass, probably for the next thermal pulse, or to see how we can just if we can just unbound up more mass or go into different regions in the parameter space of the binaries. The second thing we want to try is, the first one we want to try is going to wider separations to see if the mass ratio between the components of the binary will affect the AGB, and see if we have the post-AGB, these post-AGB binaries. And hopefully we can map these and do a similar work as SU 2020 for our post-common envelope PN. Thank you.
Thank you. That was dead on time. I didn't give you the 1 minute because I thought you'd finish perfectly. So are there any questions? Hey, Adam.
Thank you. That was a great talk. Beautiful, beautiful images. I'm wondering, just with thermal pulses, right? You change the morphology of the AGB star because of all the internal dynamics that's happening with the pulse itself. Does in any way how might the stuff that we cannot model yet, the radiation inside the star, how might that affect it, right? So the star is being reshaped by the radiation transfer within it because of the source of the pulse. Is there anything there that we think we're missing by not being able, that may really matter because we can't model the radiation transfer in the star? Just wondering.
Oh yeah, absolutely. We found that, for example, changing the artificial,
shell burning.
No, I forgot the name of the
conductivity.
Yeah, thank you. Vertical conductivity changed. Sorry, changed greatly how first of all changed the stability of the star, then also
Right.
changes whether you can have these, I don't want to say shocks because it's really difficult to model shocks on SPH, but these regions where you may have shocks in a physical, in an actual binary, and it's really hard to model. The other thing is that, well, partially I can answer also that the fact that we also make a model with pressure, radiation pressure, and that doesn't seem to affect that much in this region because we have a 2 solar mass star, which it doesn't really amount to that much in radiation pressure. Now, I'm not sure about how well the radiation will affect regarding those aspects. The other thing I can tell you is that, well, it will definitely affect, but I will be more worried about the optical depth of the whole gas, more about the radiation. I think that's a little bit more player in this kind of simulation, that the radiation, the radiative transfer.
Okay.
Thank you, Miguel.
Because
Raghavendra, can you do super fast?
Yes, so I have a quick question. You said that you could eject about 82% of the common envelope mass if all the recombination energy was trapped. But presumably different, depending on your simulation, you could let different amounts of recombination energy leak out, which would then say that you could eject anywhere from 0 to 100%, close to 100% of the common envelope mass. Is that correct? Or?
Well, not exactly. I did say that recombination plays an important role, but the bound mass that I calculated, that's 82%, it was just taking in consideration the mechanical in my simulation. Actually, I can show you a little bit. Actually, here I have to say I made a mistake because I was a small mistake because I was meant to put the bound mass for the ideal and the MESA one. I just repeat the MESA one for some reason. But here you can see the criteria for potential and kinetic, which is the mechanical one, is the blue one. It's around 0.2 solar masses, and the initial value is around 1.14. So if you quickly make the math of how much bound mass has been, how much mass has been unbound, around 82 using that criteria. I'm not using recombination for that one. I'm using the lower value because going a little bit further than that is really tricky. If I use the whole value, of course, you will have like 99%. But I was using that value before, but I stopped using it because it's not trustful.
Thank you.